In this video, I'm going to define the terms stability and accuracy, and discuss 4 features of numerical schemes that affect the stability and accuracy of their solutions. Numerical diffusion, which was discussed in depth in a previous video, bounded solutions, the Courant-Friedrich-Loewy or CFL condition, and linear stability analysis. Suppose we have a variable c that depends on 2 independent variables x and t, and we have a numerical scheme defined at discrete points I delta x and j delta t, and a problem defined between time 0 and capital T. The numerical scheme is stable if its infinite set of computed solutions, c of I delta x j delta t, is uniformly bounded for any time step between 0 and t. We should note that consistency and stability are entirely different conditions and should not be confused. A full discussion of consistency can be found in my video on consistency in numerical diffusion. As delta x and delta t tend to 0 with a fixed ratio, a stable solution stays uniformly bounded, while an unstable solution exceeds the bounding value. We'll look at what this means through examination of the classic first-order upwind finite difference solution to the advection equation. Here we have the first-order upwind explicit scheme for the advection equation, for which we must have u greater than 0 to preserve the upwinding. In the video on consistency in numerical diffusion, we saw that the truncation error of this scheme is given by this equation. We also saw that the first-order terms could be written in terms of d2c by dx squared, giving this equation, which highlights the way that the first-order terms resemble a diffusion term. This causes 2 distinct effects. If the Courant number is less than 1, the numerical diffusion coefficient is greater than 0, and we have some numerical diffusion effects, i.e. a reduction in peak value and increase of lower values. If the Courant number is greater than 1, then the numerical diffusion coefficient is less than 0, and we expect negative diffusion, which means that the peak values will increase. Over a number of time steps, that increase will make the solution unstable, as the peak values will not be uniformly bounded. Let's look more closely at the case where the Courant number is less than 1, and consider the calculation at node I on the x-axis at time step j plus 1. On the finite difference grid, we can see our 3 calculation points and the domain of dependence of the update equation. Let's define 2 constants, a and b, as 1 minus rho and rho respectively. Then the equation for Cij plus 1 can be written a Cij plus b Ci minus 1j. If we take whichever is larger of Cij and Ci minus 1j, it's clear that Cij plus 1 must be less than a plus b times this larger value, which can be written formally like this. Now we also know that a plus b is 1. Thus Cij plus 1 is less than or equal to the larger of the 2 values at time step j. We can say it is bounded by those 2 values. If we now look at the calculation at point ij, we can make a similar argument, giving us a condition for Cij being less than or equal to the larger of Cij minus 1 and Ci minus 1j minus 1. Repeating for point Ci minus 1j, we see that Ci minus 1j is less than or equal to the larger of Ci minus 1j minus 1 and Ci minus 2j minus 1. We can combine these 3 inequalities and see that Cij plus 1 is less than or equal to the largest of the 3 values at I minus 1 and I minus 2 at time step j minus 1. Taking another step back in time, we can see that Cij plus 1 is less than or equal to the largest of the four values at I minus 1, I minus 2 and I minus 3 at time step j minus 2. We can repeat this procedure and keep going back all the way to time step j equals 0, giving us this inequality. This tells us that any solution is bounded by the initial and boundary conditions. We turn our attention now to the Coulomb-Friedrich-Louvre condition, or CFL condition. We know that hyperbolic partial differential equations have characteristics in the xt plane which have a slope of 1 over the celerity. We also know that information propagates along the characteristic. In the case illustrated here, the numerical solution is unable to capture the solution to the differential equation because the characteristic is not contained within the computational cell. The time period that information takes to cross the cell is delta x times the gradient, i.e. delta x divided by the celerity. In this case, delta t is greater than this period, and we have the condition celerity times delta t over delta x is greater than 1. This has an amplifying effect and results in an unstable solution. In the case where delta t is less than or equal to delta x over the celerity, the characteristic is within the computational cell, and there's no amplification. This results in a bounded solution which is stable. This is known as the CFL condition. In the case of the advection or transport equation, the celerity is simply the velocity of the flow, u, and we have the condition for stability that the current number is less than or equal to 1. For the Saint-Venant equations, we have a celerity of u plus or minus root gh. Since u plus root gh is always larger than u minus root gh, the CFL condition becomes u plus root gh times delta t over delta x is less than or equal to 1. We are now going to look at one mode of analysis for establishing whether a scheme is stable or not, and for establishing stability criteria for numerical schemes. It is known as von Neumann stability analysis, named after the great Hungarian-American polymath John von Neumann. It's also referred to as the Fourier analysis method because it's based on Fourier series. The method is strictly only applicable to linear equations, but in practice is also applied to nonlinear equations by linearizing first. So let's consider a solution generated by a numerical scheme. In the illustration shown here, we have 5 time steps, t1, t2, t3, t4 and t5. Consider the solution at a point on the grid with coordinate m delta x. Note that here I've used m to denote the node, since I'm going to use I to denote the square root of minus 1. We will of course have a value of c at this node for each time step, which will be denoted cmj. Let's assume that there are n cells along the x-axis, i.e. n plus 1 discretization points. We're going to write the solution to the numerical scheme as a Fourier series, which will be of this form. As we can see, each Fourier series has n components. This is because the number of discretization points per wavelength can't be resolved for higher wave numbers. If we look at the first component of the series, k equals 1, it will be a curve like this, which is half a wave, which thus has 2n discretization points per wavelength. For k equals 2, we have a single wave and nx is n. When we get to k equals n, we have a value of nx of 2, which is the smallest number of points per wavelength that is possible to resolve. Let alpha denote the non-dimensional wave number of the kth component, defined as k pi over n. Then k pi x over L can be rewritten simply as alpha times m, and cmj can be written as shown here. To perform the stability analysis, we substitute the Fourier series expansions into the numerical scheme. Consider the first-order upward explicit scheme for the advection equation. We have in this equation Fourier series for Cmj plus 1, Cmj and Cm-1j. We substitute these into the finite difference equation and consider only the kth component of the resulting Fourier series, giving us this equation. We can divide this by e to the I alpha m, giving us this relationship between the amplitudes zeta kj plus 1 and zeta kj. We can now define an amplification factor as we go from time step j to j plus 1 as the ratio of amplitudes zeta kj plus 1 and zeta kj. This gives us 1 minus rho plus rho e to the minus I alpha. The exponential term can be written in terms of trigonometric functions, giving us this equation for the amplification factor. We can now separate the real and imaginary parts, allowing us to find its magnitude. The requirement for stability is that the magnitude of the amplification factor is less than or equal to 1. If this is the case, then the amplitude for every component at any time step does not exceed the amplitude of the same component at the previous time step, providing a solution that is uniformly bounded. It's informative to examine this using an Argon diagram, which is obtained by plotting A in the complex plane. Let's look first at a current number less than 1. As an example, I'll take rho equals a half. Our equation for A becomes A equals a half plus a half cos alpha plus I times minus a half sine alpha. Here we have the complex plane. Plotting A in this case results in a circle centred on the real axis at 0.5 with a radius of a half. The maximum magnitude of A occurs on the real axis at A equals 1, i.e. the magnitude of A is less than or equal to 1 for all alpha. If we look at a current number of 1, our equation for A is cos alpha minus I sine alpha. This is a circle centred at the origin with a radius of 1, and the magnitude of A is exactly 1 for all alpha. Finally, for a current number greater than 1, taking rho equals 1½ as an example, A is given by minus a half plus 1½ cos alpha plus I times minus 1½ sine alpha, which gives us a circle centred on the real axis at minus a half with a radius of 1½ In this case, the minimum magnitude of A occurs on the real axis at A equals 1, and the magnitude of A is greater than or equal to 1 for all alpha. We can see from the Argon diagram that the magnitude of A is less than or equal to 1 when rho is less than or equal to 1, which proves that the scheme is stable if and only if rho is less than or equal to 1. Performing this type of analysis thus provides us with stability criteria that we can use to help us choose our numerical parameters when running a model. Let's have a look at the stability criteria for a couple of other finite difference schemes. The first order explicit scheme for the one-dimensional diffusion equation is given by this update equation. This scheme is stable for a Fourier number less than or equal to a half. The corresponding implicit scheme for the diffusion equation with weighting theta across time steps is given by this equation. This scheme is unconditionally stable when theta has a value of a half or more, and for smaller values of theta is stable provided that the Fourier number is less than or equal to 1 over 2 times 1 minus 2 theta. The quickest scheme for the advection diffusion equation, when u and d are both greater than 0, is given by this equation. This case is a little more complex, but von Neumann's stability analysis gives us an equation for the amplification factor. We have this equation. Given a particular set of parameters, we can plot an Argon diagram. Here we see an example in which ρ is 1 and r is a half, and we can see from the Argon diagram that the magnitude of A is less than or equal to 1, so the scheme is stable. Let's keep the same values of u and d, but change the numerical parameters to see what happens. Here we have ρ is 0.8 and r is 0.4, and the Argon diagram has quite a different shape, but the scheme is still stable. Again, for ρ equals 0.6 and r equals 0.3, we have a stable solution. Just to give an example of an unstable case, here we have the case ρ equals 1.1 and r equals 0.6. And it's clear from the Argon diagram that we would expect instability with this choice of parameters. Returning to the case ρ equals 1 and r equals 0.5, let's see what happens if we keep ρ as 1 and change r. First, let's look at r less than 0.5. Here we have the case ρ equals 1 and r equals 0.4, which is clearly stable. For r equals 0.3, the Argon diagram looks like this. R equals 0.2 gives us this. R equals 0.1 gives us this, and we can clearly see that the modulus of A is approaching 1 as R decreases. Finally, as R reaches 0, the case where there's no diffusion, we can see that the amplification factor is exactly 1 for all the wave numbers. Going the other way, if ρ is 1 and r is greater than 0.5, we get unstable solutions. Here we see the Argon diagram for the case r equals 0.6. However, it's not as straightforward as simply requiring r is less than 0.5. Here we have the case ρ equals 0.8 and r equals 0.6, by way of illustration of another stable combination. It should be clear from this that if we're going to use this scheme, we need to choose ρ and r carefully. Using a spreadsheet to plot the Argon diagram can be a useful way to do this. Alternatively, if you write your own code, you can run a check on the magnitude of A for all values of the non-dimensional wave number alpha within your code. Finally, we move on to accuracy, which is distinct from both consistency and stability. The accuracy of a numerical scheme is a measure of how well the scheme approximates the results of the differential equation it's supposed to model. The amplification factor, derived from von Neumann or Fourier series analysis, is one way in which we can assess accuracy. The amplification error is the error described by the amplification factor. When the magnitude of the amplification factor is 1, we expect there to be no amplification. We should note here that this doesn't necessarily mean that there's no error in our numerical model. If it's greater than 1, then we have amplification of the numerical solution. And if it's less than 1, then we expect attenuation, which is a dampening or diffusive effect. We saw in my previous video on implicit schemes for the advection equation that there's another type of error that's observed in some numerical schemes, the phase error. Here we see results obtained using a first-order upwind Crank-Nicolson scheme for the advection equation with a Courant number of 4. We see that the numerical solution has a lag when we compare it to the exact solution. The wave is travelling at a lower velocity than the actual celerity. The phase error is the error causing different components to propagate with different celerity. We usually see it as a deformation of the propagated wave, like that we just saw in the advection example. Reminding ourselves that the amplification factor is the ratio of the amplitudes from time steps j to j plus 1 at a point in the Fourier series representation of the solution, we define the celerity ratio as minus the argument of A divided by alpha times the celerity, where the argument of A is the angle that the line joining the origin to A subtends with the real axis in the complex plane. For example, for the first order upwind explicit scheme for the advection equation, we know that A is given by this equation. And we've already seen that we have an Argon diagram like this for ρ less than 1. The celerity ratio in this case is minus arctan ρ sine alpha over 1 minus ρ plus ρ cos alpha divided by 2 pi u over nx. We can see from the Argon diagram that for this case, the closer ρ is to 1, the closer arg of A is to alpha. In summary then, we looked at two aspects of numerical schemes, stability and accuracy. We saw that we defined a scheme as stable if its infinite set of computed solutions is uniformly bounded, which is to say it produces results within the bounds of the range of the initial and boundary conditions, in the same way that the results of the differential equation being modelled does. Instability, on the other hand, produces results out of that range, and that usually tells us that something's wrong with the way the numerical calculation has been set up. We looked at the CFL condition for hyperbolic PDEs and examined how we can analyse stability using von Neumann or Fourier series analysis. We then discussed accuracy, which is a measure of how well the results of the numerical scheme match with those of the differential equation that it approximates. And we looked at what the amplification factor derived using Fourier series analysis can tell us about accuracy. First in terms of amplification or attenuation, and lastly in terms of phase error, which is an error that causes different components of the solution to propagate with different celerity, usually resulting in deformation of the propagated wave. We also noted that stability and accuracy are both distinct from each other and from consistency, which is the property that the numerical scheme tends to the original differential equation when the discretization steps tend to 0. For example, it's possible to generate a numerical scheme that is consistent but unstable, or a stable, consistent scheme that is not accurate.